Welcome to your next booklet, which is acids and bases. Before you watch this video, you should have already watched the previous video on the introduction to acids and bases from YouTube, and then you're going to watch this one from Mr. Ginsberg. Please, before you start, just cross out the incorrect date. We are now in May, or depending on when you're starting this, May or June 2020. We are using last year's notes. So originally the word acid applied to substances that had a sour taste. So vinegar, lemon juice, grapefruit and sour milk have all got sour tastes because of the presence of certain acids. And it's those acids present in the animal and plant material that we call organic acids. So in order to get carbon dioxide, it comes from carbonic acid. So carbonic acid from carbon dioxide dissolved in water is present in fizzy drinks such as Coca-Cola. Those of you that have maybe got a soda stream at home, what that does is it actually dissolves carbon dioxide gas into water, and then you've got sparkling water or soda water. And then if you add flavor into it, then you can have soft drinks like Coca-Cola and Fanta and so on. But all sparkling water or soda water is just carbon dioxide gas dissolved in water, and that particular acid we call carbonic acid. So these acids, the acids that are present in these circumstances, are weak and dilute. I often drink sparkling water and I survive, even though I'm drinking carbonic acid, but I wouldn't drink other acids that are strong acids like hydrochloric or sulfuric acid, because they would kill me, they'd burn my tongue. So please do not taste just any substance, because some acids are dangerous to taste. Many acids are corrosive. You learned about corrosive substances when you did working in the lab. There's even a symbol for a corrosive substance. If you've already forgotten what that is, best to go back and refresh your memory. So corrosive acids can eat their way through clothing and are dangerous if they come into contact with skin. That's why we wear safety goggles and a lab coat and gloves. Sometimes I've been working with sulfuric acid and I didn't have a lab coat on, and my clothes have been ruined because of it. And it really does burn your skin, so that can be really, really dangerous. You need to be very careful when you're working with corrosive acids. Some acids can attack stonework, like marble statues or marble counters and so on, and other acids can also attack metals. Those powerful acids we often call mineral acids. Mineral acids. So there is a table of some acids. You do need to know the names of these acids, and some of them you do need to know the formulas. You don't need to know the formula for lactic acid, but the rest you do. The rest of the formulas you do need to know off by heart. So ethanoic acids found in vinegar, the formula we say is CH2, CH3COOH. Methanoic acid, HCOOH. Citric acid, C6H8O7. So we've got 6 carbons and 8 hydrogens and 7 oxygens in citric acid. What you should be realizing though is that every single acid contains a certain element. See if you can recognize what that element is. If you said hydrogen, you'd be right. So hydrogen, 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 hydrogen. Okay, so all of these acids contain the element hydrogen. All right. Now let's have a look at the particle diagrams and formulas for certain acids. So hydrochloric acid, the formula for hydrochloric acid, you should already have an idea of what elements are in hydrochloric acid just from its name. So hydro implies we're going to have hydrogen, and chloric implies we're going to have chlorine. And then there's the formula for it up there as well. And a particle diagram, if I give you a key and I say that you have to use a solid dot for hydrogen and a circle with vertical lines for chlorine, then you'll have to use that exact key. So try and draw in a particle diagram on your own for hydrogen, pause the video and then stop it once you're done. What I'm going to do is make the size of this hydrogen atom a little bit smaller, because hydrogen atoms are actually smaller than other atoms. So I'm just going to make it slightly smaller, but I'm still going to keep it as a solid black dot. Right, so particle diagram. There's my solid black dot to represent the hydrogen atom. And then I need to have a vertical, also a black dot, but with vertical lines in it, to represent chlorine. So there's the particle diagram for hydrochloric acid. The acid with the formula H2SO4, sulfuric acid. So that's sulfuric acid, and its particle diagram, we're going to use oxygen to have an open circle, sulfur to have a circle with little dots inside it. So let's start with that. So sulfur is a circle with dots inside it, and then we need to have 4 oxygens and 2 hydrogens. So oxygen is just an open circle. 1, 2, 3, 4. And then we also need to have 2 hydrogens. 1, 2. So there's the particle diagram for sulfuric acid. And nitric acid, formula for nitric acid is over here, HNO3. So 1 nitrogen, 1 hydrogen. Remember, there's invisible ones there, but we don't actually write them. 1 nitrogen, 1 hydrogen, and 3 oxygens. So let's start off with the nitrogen. The symbol that they've asked us to use is a circle with horizontal lines. So there's our circle with horizontal lines. And we need to add on 3 oxygens. Try and make these diagrams as symmetrical as you can, because that's how the molecules will actually look. Okay, 3 oxygens and 1 hydrogen. That hydrogen you can't put anywhere to make the molecule symmetrical. It's going to be asymmetrical, so it doesn't matter where you put that extra hydrogen, so long as the hydrogen is slightly smaller than the other atoms, because hydrogen is a smaller atom. So these acids, we can even add in over here that these are strong acids. Because they are strong acids. You'll learn more about that in grade 10, strong acids. Okay, now let's look at bases. So in the previous video that you watched, you would have learned about acids and bases. We've spoken about acids. Bases can also be very dangerous. So let's talk about sodium hydroxide. Sodium hydroxide, the formula is obviously going to contain sodium. And the hydroxide group is known as the OH, or the formula for the hydroxide group is OH. Okay. Particle diagram, please make hydrogen a little bit smaller, because it is a smaller atom. Okay, so we need to have 1 sodium, and the formula for sodium is shown over here. So a circle with diagonal lines in it. So there's our sodium atom. Then we need to have 1 oxygen. Oxygen from above here. Oxygen's got just an empty circle. And then we need to have a hydrogen. In tests and exams, either will give you a key just like we have over here and tell you what symbols to use for which elements. If we don't, then you get to choose your own. But do something that's quite obvious. So please don't make something, say sodium, look like that, and potassium looked like that with slightly bigger dots, because then it's hard to decide which you're actually meaning. Are you referring to sodium or potassium? Are the dots big or small? So use something that is quite obviously different. Okay, if sodium hydroxide had the formula NaOH, then calcium hydroxide is going to have the formula CaOH. This number here, this 2, means that we've got 2 of the OH groups. So this is calcium hydroxide. Calcium, we're going to use the symbol, there it is, circle with also diagonal lines, but diagonal lines going the other way. Okay, so there's our calcium atom. Then we need to have 2 oxygens. So what this means is that we've actually got calcium, OH, and another OH. So instead of writing 2 sets of OH, we replace it just with a 2. But that's what it actually means. Oxygen, oxygen, and then we need to have 2 hydrogens as well. There's our hydrogens. So that's calcium hydroxide, also a strong base. And then the last one is ammonia. Ammonia's formula, you should remember from your last notes, your basic chemistry notes. Ammonia's formula is NH3. So 1 nitrogen, 3 hydrogens. Formula for nitrogen, horizontal lines inside a circle. With 3 hydrogens. 1, 2, 3. Okay, so those are the particle diagrams for our bases, and there's the particle diagrams for our acids. So you do need to know the formulas for them and their names. What do you notice is common to the formula of all of the acids? I already told you they all contain hydrogen. I can't tell you this for all bases, but most bases do contain this OH group. But there is an exception, which is ammonia. There are 1 or 2 other exceptions as well. But most bases do contain the OH group, whereas acids don't contain OH, they've just got a hydrogen. They can have oxygen like sulfuric acid, but it's not an OH group in the form of, like here where we've got sodium hydroxide with that OH group. There's an OH group, there's an OH group. Okay, there's a research assignment for you to do. So you're going to find the name, formula, and use of 1 other organic acid, and then draw a particle diagram for this acid that you've got. So there are many that you can Google. So you're going to have its name, the formula, the use, and then a particle diagram. Remember to put in a key. Please don't pick something that's really complicated that's going to take you hours to draw. So just a smallish molecule is fine. There are a lot of natural acids, so you can research what birds or wasps' stings have got in them. Not birds, bees and wasps have got acids in their stings. Fruit has got different acids in fruit and vegetables, so you get to do that. And then you also get to do one for a mineral acid. So 1 for an organic acid, 1 for a mineral acid. And each of you will have your own different answers for that. If you want, you're welcome to send, in fact, not if you want, please do send this for homework. Once you've done it, send it to your teacher, and they can check that you have done it. In your next lesson, we're going to look at indicators. In the previous video that you watched, though, you did get a little bit of an introduction to indicators. But this is your homework, just to do the research assignment and then send it to your teacher. Thanks, Gr8. Bye.